Welcome to Spring LIB.
Okay, so we're trying to find the thickness needed for a coating applied to glass, and we want to eliminate these different reflections. So let's get started. And then we know, let's write down that n is 1.38, and then, yeah. So to draw our picture. So for anti-reflection, actually, let me finish drawing. So this is glass. I think glass is usually has an index of refraction of around 1.5. I think it's usually bigger than the coating. Let me just double check. Index of refraction of glass. Yeah, it's around 1.5. So let's just go with that. So then we're concerned with the interference between a photon coming in and reflecting off this surface and the photon coming in, traveling through here and reflecting off here. So we want to get the phase difference between the two. And if we don't want them to reflect, we want to set that phase difference. So that's going to be, so let's call this photon 1 and this photon 2. That's going to be the phase of photon 2 minus the phase of photon 1. And this delta lambda, if we want it to be destructive, we want it to be 2n m minus 1 times pi. This is just to express it. We want an odd multiple of pi, because odd multiples of pi, if that's the phase difference, then you'll get destructive interference. So m is going to be an integer. And then now we need to come up with phi 2 minus phi 1. So phi 2, that's going to undergo the phase shift of going through the glass, or excuse me, the thin film. That phase shift is going to be 4 pi n t divided by lambda. And that just comes from the general idea that the phase of a sine wave is going to be, the spatial phase is 2 pi over lambda times x, and then x is going to be 2t, and then lambda goes to lambda over n, so that's how you get that. And then any other phase shifts? Well, yes, phi 2 is going to reflect off of this, so it's going to have a pi phase shift, so we can do plus pi. And then now let's look at phase 1. Well, phase 1, or photon 1 is going to have a 180-degree phase shift, so it's going to be minus pi. So that's kind of nice. These cancel. And so now we are left to solve for the thickness. So the thickness is going to be lambda. The thicknesses which would produce destructive interference is lambda 2m minus 1 divided by, I'm trying to do this math in my head, for n. And then that's going to be, oops, this needs to be n of the film. So let's just call that nf. And so now we want the thickness to be, they want the smallest thickness. So we want this, so we want to basically choose the smallest odd number. The smallest odd number is 1. So that's just going to be lambda over 4nf. And so we can do this for the different lambda. So I'm just going to kind of write these as a set. So for lambda is, let's see, 450. We want to do 450 divided by, what was it? 4nf divided by 4 times 1.38. And then with that, I get 81.5 nanometers. I'll just go 80, because there's 3 sig figs, I guess. But the 450, let's say it has 2 sig figs. So then, drum roll, let's just use 2 sig figs. So that's 82 nanometers. And then for the other ones, let's see, now we want to plug in lambda 720, or just the other one, I guess. So now let's do 720. I must do that in my head. And that's going to give us 130 nanometers thickness. That's really thin. I wonder if that's actually what the thicknesses that they are. Oops.